Hello everybody and welcome back to part 2 of deriving the Friedmann equations. Last week we ended off having derived various tensors and doing other setup to actually get to the crux, or the zenith of the derivation, which is the actual derivation, which is what we're going to do today. If you haven't seen the video from last week, I would urge you to go and watch it, otherwise bits and bobs might not make sense to you. It was quite a long video, and it will definitely help. I doubt this one will be as long. There's less stuff going on. Oh, thank you, Windows Defender. Right. Anyway, so we've got a load of stuff, and we can start using it, and we'll use it in the Einstein field equation, Z, which is 8 pi gt sub mu nu. I have a video on this, and if you're interested, you should definitely go and watch it. But let's find the first equation, which is mu nu equals 0, which is the 0, 0 component. So then we have g0, 0 is equal to 8 pi gt 0, 0. Let's substitute in equations. So for g0, 0, we should have up here that g0, 0 is 3a dot plus k over a squared. And we also have that t0, 0 is rho, from the energy momentum tensors rather. So subbing that in, 3a dot plus k over a squared is equal to 8 pi g rho. We can pull 3 out and then a dot plus k over a squared. Not pull it out, we can divide 8 pi g rho over 3. And I'd like to expand this, so it's a dot over a squared plus k over a squared. That's equal to 8 pi g rho over 3. And this brings us, well, we already have our Hubble parameter. I'm not going to scroll all the way up, it's quite far up, but that being a dot over a. So we can restore C here, and it holds that h squared is equal to a dot over a all squared, which is, using this, 8 pi g over 3 times rho minus k c squared over a squared, just to make our naturalized units function. What does this mean? So the first Friedmann equation, which is this, it relates the expansion rate of the universe to its content of energy, and then its geometry. It's like the analog of the energy equation, which is half a dot squared minus 4 pi g rho a squared over 3 is minus k over 2. Essentially, half a dot squared is our kinetic energy, and 4 pi g rho a squared over 3 is our potential, and k is the total, or rather minus k over 2 being the total. So that's essentially what we've got there. This is number 1. I will box it. We'll move on to number 2, which takes slightly more time to get to. So here, of course, well, not of course, but we're gonna find the 1, 1 component, which is mu nu equals 1. And so we have that g11 is equal to 8 pi g t11. And again, we can substitute in g11 and t11 from above, and we get that minus 2a dot dot plus a dot squared plus k over 1 minus k r squared equals 8 pi g times PA squared over 1 minus KR squared. Things being over 1 minus KR squared gives me nightmares. Anyway, we can in fact get rid of it, which is nice. And I'll move the minus to the other side as well. So we have 2a double dot plus a dot squared plus k is equal to minus 8 pi GPA squared. That being a p, not a row. What we can do is then plug in our first Friedmann equation to eliminate this a dot plus k, a dot squared plus k rather. So we get then from rearranging this that a dot plus k, a dot squared plus k is equal to 8 pi g p a squared over 3. And we can throw this back in, so 2a plus 8 pi gpa squared over 3 a is equal to minus 8 pi GPA squared. Things will of course cancel out. We can get rid of a 2a squared from each side, or rather I'll move this to the other side first. 2a double dot is equal to minus 8 pi GPA squared minus 8 pi GPA squared over 3. This is a row. I was like, you shouldn't be able to cancel this out because I've written terrible notes, and this is not p, this is row. That's row and that's row. That makes more sense. Row, row, and row. Now we should have that. This is minus 8 pi g a squared p minus row over 3. And then we can divide both sides by 2a, which will give us that a double dot over 2a squared even, because then we have our a dot over a is equal to minus 8 pi ga squared, no, just g, no a squared, over 2, or just 4, p plus row over 3, which is minus 4 pi gp plus row over 3. And then we can restore our c. And so we have that a double dot over a is equal to minus 4 pi g over 3 row plus 3p over c squared. No, box. Nice, and this is that was the world's worst box I think the world has ever seen. That's what the world's worst means. So this is the second Friedmann equation. It's also, oh god, I'm not going to pronounce this right, Raychaudhuri equation. Anyway, it's basically, it's the acceleration equation for our expansion. So this is important because we have energy density rho and pressure P both sourcing like gravitational deceleration. This is relativistic and purely relativistic. In Newtonian gravity, only mass can decelerate the expansion, but pressure acts as a source of gravity, which is obviously non-Newtonian concept. For any ordinary matter where P and rho are both bigger than 0, that's going to give us an acceleration less than 0. So gravity decelerates the expansion there. But there is an accelerating expansion, which is where P is less than minus rho c squared over 3. Well, that's negative pressure, which is a cosmological constant, which may or may not exist. But yeah, that would be the condition for accelerating expansion. Now we have one more equation, so these two are the actual Friedmann equations, and then there's one more, which is our continuity equation, because Friedmann just thought, let's combine relativity and fluid mechanics. So of course you're going to have momentum in very, very big inverted commas, and continuity in less big inverted commas equations. So we have something called the fluid equation. And how do we derive the fluid equation? Well, these aren't independent. So we have a conservation of the energy momentum tensor, which gives us an additional relation, and we can take the nu equals 0 component, giving us mu t mu 0 plus gamma mu lambda to mu t lambda 0 plus, it's just 0 mu lambda t mu lambda. I'm doing it again. I'm doing my lambdas the wrong way around. Why would anyone ever do this? As a tick. But it's not, because it would be that. And then that would become that. So it actually would just be, that would be, no, but it's flipping about that axis. So no, it would be a tick, but like a, no, that's not a tick. Okay. Enough. You can, I don't want to, I mean, I think it's fairly simple to do this. You're just subbing in more things. You sub back in all of the Christoffel symbols and with the FLRW metric, and that yields that rho dot plus 3 a dot over a rho plus p over c squared is equal to 0. That coming from all of this. Well, this is just conservation of energy, but really big. So 3a dot over a is 3h. This is the fractional rate of volume expansion. So if you have a sphere of radius a, it'll have a volume of a cubed. So dv dt, or of just d dt of ln v is 3 of a dot over a. And that's where that comes from. The rho dot term, this is minus 3h rho plus p over c squared, which is the last bit, or rather just rearranging. What does that mean? Well, the rate of change of energy density is minus the expansion rate times the enthalpy density, which is scary chemistry words. But again, it's to do with energy. And well, we can see what happens as well for pressureless and the pressureless matter. Yeah, first of all, so rho dot would simply be minus 3h rho. Rho is proportional to a to the minus 3. What does that mean? Well, density gets more diluted as the volume grows, because obviously your change in volume is proportional. Change in density is proportional to current density. And then radiation, which is more applicable slightly. We take P as rho times c squared over c. Then we get that rho dot is minus 4h rho. Rho is proportional to a to the minus 4 this time. Where does that come from? Well, we have a redshift factor of a to the minus 1. And what if we had a cosmological constant, and in which case rho would be, p would be minus rho c squared, negative energy density. Then rho dot is 0, and rho is just a constant value. Well, what what can be shown by differentiating the first Friedmann equation and by differentiating the fluid equation. It can be shown that the second Friedmann equation follows from the first and the fluid equation. So the system has two independent equations, which are the first Friedmann equation and the fluid equation, plus essentially an equation of state, which is, I should have boxed this, which is our second Friedmann. I might write them all out in summary as well in just a second. Which is this middle equation is just an equation of the state of P being P of rho. So, well, that was a bit of a saga. In conclusion, we have the Friedmann equations to be the following. That a dot over a squared is 8 pi g over 3 rho minus k c squared a squared. Secondly, that a dot dot over a is equal to minus 4 pi g over 3 times rho plus 3p over c squared. And then finally, with conservation, that rho dot plus 3h rho plus p over c squared is equal to 0. I will put these in. I might try something actually, which I've never tried before, and I'm curious as to how it will end up looking. You can. Oh wait, what if I just wait? Lock in. Oh yeah, that's brilliant. And then I can like probably shift it around a bit. Yeah, nice. Okay, well that's my fancy improved box. And that was the derivation of the Friedmann equations. They, yeah, under the assumptions that the universe can be treated as some isentropic, homogeneous, like fluid of energy, then yeah, we can derive these important equations that explain expansion and possible contraction of the universe via the cosmological principle. So, shorter video today. I hope that you enjoyed reaping the rewards of the pains of last week's video, and I'll see you next week for something new. Anyway, goodbye.